Hello, hi. So, um, linear algebra. You've done this before to some extent, but probably only very restricted versions of this. But linear algebra is a very important branch of basic mathematics. Simply put, it's the study of linear equations. I'll get back to what linear and nonlinear equations are in chapter 10. We're going to start with some basic stuff in chapter 9 first, okay? Um, but linear algebra is used everywhere. I mean, it's a really, it's a very good thing to have in your toolbox. Uh, mm, we'll see that it's quite a bit used in computer graphics. I've talked about error correcting codes before. Um, so this is also used there. Uh, hello, why are you not working? Yes. Optimization problems, linear algebra is fundamental there. Database theory, and so on and so forth. And it's just it's a very basic um, tool that's used in many places. Okay, so in this chapter, chapter 9, so there are two chapters to part 3, chapter 9, chapter 10. In chapter 10, we'll see how to use what we're going to discover or introduce in chapter 9, how to use that to solve systems of linear equations. And then after that, we'll talk about computer graphics. But I need to define some basic tools first. So, I mean, you've been doing some programming, certainly, and you have probably used arrays at some point. So we're going to talk about arrays in linear algebra. They're called matrices. We'll talk about matrices and vectors and some basic operations on matrices and vectors. So again, you certainly have seen parts of these things in maybe a restricted context, but we'll see that in more generality. We'll see the notion of determinant and of invertible matrices. This will be very important when we get to solving systems of linear equations in chapter 10. So yeah, as I was saying, yeah, and we'll finish by seeing some basic applications of all of this to 2D and 3D graphics. Okay, all right. So let's start. Let's jump in. So here's a typical situation to motivate the use of vectors. You have to handle, let's say, a bunch of values. For example, the results of students on test one, on one test, okay? So you might have to compute the average or standard deviation, you know. So let's say we have 32 students. I could have picked 30. You guys are 30. But anyway, so I have these values that I'm going to write in an array. So denoted as follows. So I have W1, W2, right up to W32. So these are my 32 values listed one after another, okay? They are indexed, as you see, by, let's say, the index I. This would indicate that WI is the result of student I, okay? Sorry, I keep blanking out because people are coming in one after another. When I click to let them in, then I'm having trouble getting back to my slides. I'm sorry. So a one-dimensional array is called a vector. So this is a vector, okay? it can be useful to write this vector horizontally, just like I did in this example. This would be called a row vector, or sometimes we will write them vertically. So this would be called a column vector. We'll get back to that a little later, okay? So we can write an array like that, a vector like this can be written horizontally or vertically, so row or column vector, okay? All right, two-dimensional array. This is also useful. So typical situation, I want to handle several values, right? This is only herb tea, I swear. It's not vodka. Such as the results of students on several exams, right? So again, I might want to compute the average per student or per exam and so on and so forth. So to do operations on the columns or the rows, because this is an array you'll see in just a sec. So this is what it might look like. So let's say I have 32 students and 3 exams. So I can write the results in a table, right? An array, it's a two-dimensional array, okay? So in one column, if you look, let's say at the first column here, you have W is indexed by 2 numbers, 1, 1, 2, 1, right up to 32, 1, right? So these would be the results of my students for test 1, okay? So that would be, so the column there could be viewed as a column vector if you wish, right? In the second column, these would be the results of the same students on test 2. And finally, the third column, these would be the results of the students, the 32 students on test 3, right? Okay. So here's my array again. So how does the indexing work? If I look at W index ij, right? So you see that the first number goes from 1 to 32, and it indicates which row. So that's the student, right? So it's student I, and the J indicates the column. So this is the exam, right? So Wij, this is the result of student I in exam J, okay? So if you take row I, this will give you the results of a single student, student I, in all 3 exams, right? So the first column here, these are the results of student number 1 on test 1, 2, 3, okay? If you take now a column, say column J, this will give you the results of all the students in one exam, exam J, right? Okay, so again, this is not extremely deep, but you just want to get used to how the indexing works. You want to get used to the notation, right, of how this, okay. So here's our formal definition. First definition, a vector of dimension n. What is that? It's an ordered n tuple of, let's say, real numbers. We'll stick to real numbers. So it is our array again. So V1 right up to Vn are the components of the vector. Now you see that I wrote the vector with a little arrow on top. This is a very standard notation to indicate that you're looking at a vector. You might also see bold font. This is very common, right? But when we're writing on a blackboard, or I'll be writing on my iPad, I will usually write with an arrow on top, or maybe underline. This is also used, okay? But in books, it's often boldface, which is used, okay? So now, what you may have seen in high school or elsewhere is that vectors can be seen as something which is geometric, okay? So you can see a vector as simply a list of values, or you can interpret it geometrically if you wish, and this is sometimes useful, okay? Especially, of course, in 2 or 3 dimensions. If it's more dimensions, then the intuition is a bit more difficult, okay? But so if you have a dimension 2, dimension 3, it can be very useful to see vectors as an arrow, so a length and a direction, okay? I don't know to what extent in the book the exercises deal with that. I don't think so. When we get to the computer graphics part, of course, this will be important. But for now, I'm just trying to connect to things that you may have seen before. Okay. Okay, so now I'm going to give you like a bunch of definitions. Nothing very deep, right? It's notation and definitions. So what is the zero vector of dimension n? Well, as you can guess, this is the vector of dimension n whose components are all zero. Okay, so notice that there is a zero vector for each separate dimension. So these are all different things, right? Okay. So yeah, so two vectors, I should have mentioned that earlier, but two vectors v and w are equal if their respective components are all the same, right? So of course they have to have the same dimension, and they have to have exactly the same components, okay? So these are not like sets where the order doesn't matter. The order does matter quite a bit, right? So here's a little baby example. So 3 minus 4 and 4, 4, these are vectors with two components. They're dimension 2 vectors. They are not equal, obviously, okay? 1, 2, 3, 3, 2, 1, these are vectors with three components, or dimension 3 vectors. They are not equal because 1 is not equal to 3, right? So the two vectors are the same if corresponding components are equal. Here you just look at the first component of the first vector, it's 1, second component is 3. Sorry, the second vector, the first component is 3, right? So 1, 3, they are not the same, so the vectors are different. That's it, okay? So these are not sets. Okay, 0, 0, 0, 0 is the zero vector with 4 components. Okay, so again, there is a zero vector for each separate, for all dimensions, right? 2 dimensions, 3, 4, 5, and so on. They're all different vectors, yeah. Okay, so let's look at some basic operations on vectors. There are two, okay? Some terminology in linear algebra, we refer to real numbers as scalars, which refers to the fact that it's an object with a single dimension, right? Which is a size. So there's no direction involved, okay? So when I talk about scalars, a scalar is just a real number, okay? All right, so first operation, very simple. What are the ingredients? A scalar k, so a real number k, and a vector v, let's say of dimension n, with components v1 to vn. So I'm going to define a new vector, which is called kv, right? And how do I define this? You take the vector v and you multiply each component of this vector by the number k, by the scalar k, okay? So this is just a definition, okay? So that's what it is. Okay, second operation, very simple also. It's the sum of vectors, okay, the plus. So ingredients now, two vectors, v and w. I just call them v and w. It could be any name, but I have to write it down, so we choose v and w. They must have the same number of components, otherwise this does not make any sense, okay? So I can add two vectors of the same dimension, okay? So here I have two vectors of dimension n. How do I add them? The definition is as follows. So how do I denote this vector? It's v plus w. Yes. No, the dimension is the number of components. Yes, that's exactly it. Okay. So v plus w is obtained how you add the components of the two vectors so first components together, second components together, third components, and so on. So you add component wise, okay? So that's the sum of two vectors. I'm not telling you why we're interested in this. I will tell you in just a sec, okay? But it's a very natural, it's obviously a natural operation, right? So let's see some examples. Okay, so I have two vectors of dimension 3, or with 3 components. I have v, which is the vector 2, 3, minus 4, and w is the vector 1, minus 5, 8. Then their sum, what do you do? Well, 2 plus 1 is 3. 3 plus minus 5 is minus 2. Minus 4 plus 8 is 4. So I've added components, respective components, and I get the new vector v plus w. What is 5v? Right? So what do? I multiply each component of v by 5. So 5 times 2 is 10, 5 times 3 is 15, 5 times minus 4 is minus 20. So that's my new vector, 10, 15, minus 20. Okay, so from a computational point of view, this is very, very, very simple. Okay, so these are the two basic operations we have on vectors. Okay. All right, yes, and I repeat again, you cannot add vectors if they don't have the same dimension, right? It doesn't make any sense. It is not defined, okay? All right, a bit more notation here, but it makes perfect sense given these two operations we've defined, okay? It seems reasonable to define the negative of a vector as follows. So if I have a vector v whose components are v1 to vn, then minus v is the vector whose components are minus v1, minus v2. So you multiply each component by minus 1, okay? So that's, and by extension, I can define the subtraction of vectors, right? What is that? If I have vectors v and w, then v minus w, what is that? That's v plus minus w, right? So you multiply each component of w by minus 1, and then you add these two vectors. Or if you think about it, just 3 seconds, of course, it's the same as subtracting components, right? It is exactly the same thing, okay? All right, so here's an example. If v is 2, 3, minus 4, and w is 1, minus 5, 8, then minus v is minus 2, minus 3, 4. And v minus w, well, if you just do it either with the recipe I've given you or you just subtract, right? It's the same thing. 2 minus 1 is 1. 3 minus 5 is 8. And minus 4 minus 8 is minus 12. And here's a more complicated one, 2v minus 3w. So how do you do that? Well, you multiply v by 2, you multiply w by 3, and you subtract, and you get what you see there, okay? So I don't think you're going to have any trouble with this, okay? As long as you just know what this is about, there's really no difficulty from a computational point of view, okay? All right, so far so good. All right, okay. Now, when you are doing computations on vectors, it is often convenient to write your vectors as columns. It doesn't make any difference from a conceptual point of view whether you write your vectors as rows or columns, makes no difference, okay? But by hand, often it just the way that we write, because we write horizontally, it makes sense to write them as columns. So here's a little example. If v is 2, 5, minus 3, I wrote it as a column, and w is 6, 0, minus 5, then v plus 5w, what is that? Well, you multiply, so it's v plus 5 times w, so you multiply w by 5, just multiply the components, and then you add those two vectors to get the result you see there, right? So hopefully this makes sense. I don't think that's very difficult. Okay, whether you write them as rows or columns, it's the same thing. All right, good. Okay, let's do a little sidestep here, geometric interpretation of vector operations. Now, again, this is something you may have seen. If you think of vectors as arrows, okay? So how do you think of, I don't want to go into too much details, but basically, let's say you have a vector with two components, then basically the direction is given by the number. If you start at the origin, let's say, the first component gives you how many steps you're going in the X direction, and the second component gives you how many steps you're going in the Y direction. So of course it gives you a direction, right? And if it's 3 dimensions, then you have 3 dimensions. So, okay. Now, if you interpret a vector this way, then these two operations have very natural geometric interpretations. The first one is the super easy one. When you multiply a geometric vector by a scalar, it means you're scaling the vector. You're shrinking or expanding it by that factor, okay? So let's say you have a vector v, then you multiply it by 1.5. The new vector has the same direction, but it is 50% longer. That's exactly what it means, okay? So multiplying a vector by a scalar, it's a scaling of that, okay? So you can think of what this might mean for computer graphics. Obviously, if you're zooming in, zooming out, that's the kind of operation you want to do, okay? What about the sum? Okay, this is not as obvious if you've never seen this. It's not like super obvious what this sum does, but if you play a little bit with it, you'll see that it does make sense. So if you have two vectors, then adding them basically is the following operation. So here's a little picture. Let's say I'm adding v and w, and I'm sure you've seen this before. If not, it's okay, it's fine. But v plus w, how do you interpret that geometrically? Well, you place w at where v ends. So v is a direction, right, and a length. So you take that vector w and you place it after v. You stick it where v starts, exactly like you see on the picture. And then you complete the triangle, and that's the sum. That's what it means, okay? V plus w is that resulting vector, like that, okay? So that's a very, if you're very geometrically inclined, this is the way you want to think about vectors. And by the way, you might think, okay, this works for 2 and 3 dimensions, but what about 7? Well, actually, it's the same thing. You'll say, but wait, 7 dimensions, it's the same thing. 15 dimensions, 100 dimensions, it's all the same. It's just conceptually, this is exactly what's going on, okay? But I don't have time to go there. If you have some extra time, you can go and take a look at my Cal 3 lectures, and we talk about these higher dimensional spaces. It's kind of cool. But anyway, actually, you know what? So we weren't in confinement at the beginning of the semester last year in January. So these are lost. But anyway, they'll be online in January coming up 2021. All right. Okay, so that's the geometric interpretation of these operations on vectors. Okay. Matrices. All right. So this is really not more complicated, but the notation is a bit messier, okay? So a rectangular array of real numbers we call a matrix, like the movie. The plural of a matrix is matrices. So one matrix, two matrices. So here is a picture of a matrix in the wild. This is matrix A, and it has m rows and n columns. So we say that it is an m by n matrix, m rows, n columns. Or we say that it has size m by n. Now this is a convention. The first number gives you the number of rows, and the second number is the number of columns. We have to choose, and that's how it was chosen, okay? So could have been the other way. That's the way it is. Okay. The numbers you see in the array, these are called the entries of the matrix. That's the name we give to these numbers. These are the entries of the matrix. Okay. And how does the indexing work? Well, if you look at the picture, you see that the first number indicates the row, again, just like when we talked about the size of the matrix, and the second indicates the column. So when I talk about the entry Aij, I mean the entry which is at row I and column J. Okay, so that's the convention, that's the name, that's the notation. Okay, all right. As we did for vectors, we also have a zero matrix. What is that? Any matrix whose entries are all zero. You'll say, what's the use of this? It's a useful thing, as zero is a useful number for matrices and for vectors. Zero vector, zero matrix is the analog of the number zero, okay, which is a useful number. For each different size, m by n, you have one zero matrix of that size. They're all different matrices, right? So for example, this is the 2 by 4 zero matrix, okay? All right. Okay, now we're going to define 3 operations on matrices. The first 2 are basically those that we saw for vectors. They are the same, okay? The third one is specific for matrices in a sense. It is a bit more involved and we'll go a bit slower there because it looks very strange, okay? But let's start with the 2 easy ones. So the first one, what are the ingredients? A matrix and a scalar. And what do? You multiply each entry of the matrix by that scalar. So it's the same thing that we did when we scaled these vectors. It's the same thing for a matrix, okay? So what's the notation? The notation is right there, Ka, like that. This is the scalar K times the matrix A. What do? You multiply, you see that I started with the matrix here, and I multiplied every entry by K. So that's super simple, okay? Again, computationally, there's really nothing deep here, okay? In particular, right, I could multiply a matrix by the number -1, and since it's a bit inconvenient to write parentheses -1 parentheses A, we just write -A, right? So if you see -A, then it indicates the matrix -1 times A. How do you get that? You take each entry of the matrix A and you multiply by -1, right? Okay, good. Okay, so we saw 2 operations on vectors. I can multiply a vector by a scalar, shrinking or expanding it, right? Scaling it in general. And the other operation we saw is how to add 2 vectors. We can add matrices also of the same size. This is important, just like vectors. They have to be the same. They live in different worlds otherwise, right? So you can't add them up. So let's say I have 2 matrices, A and B. They're of size m by n, both of them, okay? How do I add them? So it looks nasty, right? If you look, there's like how many numbers are there on that slide? But in fact, all it says is this: how do I add 2 matrices of the same size? I look at corresponding entries and I add them. And you do this for each entry, right? That's all you do. So for example, you look at the first entry here, first column, first row, A11. This is first column, first row for B, and you just add them together, and that'll be the first entry for A plus B. And you repeat that for each column and row, okay? So that's all this is. So the sum of 2 matrices, it's very, very straightforward, very simple, okay? All right, let's take a look at some examples, just one. Okay, so as I did for vectors, I can define the subtraction of matrices of the same size. Rather than just rewrite the whole thing, I can use what I've done to simply write it as, so A minus B, what is that? That's A plus minus B, right? Obviously, okay? All right, I mean, obviously, it's a definition. Obviously, doing this is the same as subtracting corresponding entries. That's what I mean. Okay, so here's an example. So these matrices are 2 by 3, that's their size. 2 rows, 3 columns, right? So 2 rows, 3 columns. So 2 by 3, 2 by 3. So it's legit to add them. It makes sense. How do I add them? I add corresponding entries. So you see 1 plus 3 is 4, minus 2 plus 0 is minus 2, 3 plus minus 6 is minus 3, and so on. 0 plus 2 is 2, 4 plus minus 3 is 1, 5 plus 1 is 6. That's the sum of these two matrices, okay? Here's a combination of all we've seen to this point. So this is 2 times these are 2 by 2 matrices, right? 2 times the matrix 3 minus 1, 4, 6, minus 5 times the matrix 0, 2, 1, minus 3. So this is legit. Obviously, okay, I can multiply any matrix by a scalar, that's fine. And I can subtract, we know what that means, right? Because they are the same size, right? So how do I do that? This will be, if I compute this one, I'll get 6 minus 2, 8, 12. And then this, if I multiply this, let's say by 5, it'll be 0, 10, 5 minus 15. Then I subtract and I get the matrix, which is right here, okay? It's doing this on slides is really, yeah. I mean, I'll once we're done with test 2, we'll do more examples and I'll be able to write stuff rather than just read slides, and you'll see. Okay, all right. But I think up to this point, this is not, this, it's just basically just definitions, right? Okay. Here is a very useful notation which you might not have seen before, but you guys probably have an advantage over, let's say, regular students in science because you're programming. So this will probably make a lot of sense to you if you know what a loop is. And so this is a very useful notation called the sigma notation, which helps us write down sums of many, many things, okay? So sigma is the S in Greek. So the sigma is for sum, as in, yeah. So that's why it's a sigma. And so here is how this works. I've used an example. So let's say I want to write down the sum 1 plus 2 plus 3 plus 4 right up to 19. So it's all the numbers, integers from 1 to 19. I add them up, okay? I would like to write that in a compact form, okay? And not use those 3 little dots, okay? So here is the notation. So the sigma in that notation you see there indicates a sum, okay? K is what we call the summation index. It could be any other index, but I could have used J or I or whatever, it makes no difference. Here we use K. So K equals to 1 at the bottom there means that our indexing starts at 1, right? So think of a loop. I guess you've seen that. The 19 on top means that's where you stop. That's where your indexing stops, okay? And by definition, by convention, the steps are by 1. So if you start at 1, you go to 19, it means that K runs through 1, 2, 3, 4, 5, right up to 19, okay? Now, what's written on the right-hand side of the sigma, this is the summand. This is what you're adding, okay? So in this particular example, it turns out that what I'm adding and what I'm replacing each time, replacing 1, 2, and so on, is just K. It's the index itself. But it could be a more complicated expression. It doesn't have to be k itself, okay? So what you see there is a compact notation for the sum of all numbers from all integers from 1 to 19. So here's another one, okay? So I'm looking at sigma k equals 0 to 4k squared, okay? So this is the sum k equals to 0 to 4 of k squared. So what am I adding? The kth term is k squared. So this is what I'm adding, okay? So what do? I replace all the values, the possible values of the index in this expression, and I'm going to add them all, okay? So where do we start? We start at 0. Where do we end? At 4. So it means we're going to replace k by 0, 1, 2, 3, 4, okay? And add the results. So that's what we get. So the symbol you see, the notation you see there, is to indicate 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared, which turns out to be 30. Does that sort of make sense?
Yeah.
Excellent. Okay. All right, let's take a look at another example. So sum I equals 2 to 4 of 3i minus 1. I could have put some brackets there, but 3i minus 1 is the term that I'm adding. Okay, so what do? You take this expression 3i minus 1, and you will replace the index by all the possible values. You start at 2, so that'll be 3 times 2 minus 1, and you end up at 4. So the possible values are 2, 3, and 4. So you replace by 2, by 3, by 4, and you add all the results together, right? So this is what you get. So it's a loop, right? So if you've done loops before, hopefully this is just very natural for you guys, okay? All right. So this is the sigma notation. Why am I introducing it here? Because soon we're going to see the matrix product, and to just write down the definition of the matrix product, it's very useful to have the sigma notation. But in any case, it's a useful thing to know in general. So here are 2 more examples, which are a bit more abstract, if you wish. So the first one, sum, this is how it's read, right? We don't say sigma. We say sum n equals 1 to 4 of xn. xn, that's x index n. Think of, let's say, the entries of a vector, right? So if you are, let's say, you want to compute the average of a bunch of entries, then you might have to set up something like this, right, from scratch, to add all the entries. Then of course you divide by the number of entries, but that's something else. Anyway, so again, you look at the expression x index n runs from 1 to 4. So 1, 2, 3, 4. So you replace n by its values, 1, 2, 3, 4, and you add the results. So the first example there, that x1 plus x2 plus x3 plus x4. Of course, the way it's written, we don't know what these numbers are, but depending on what they are, we could get the sum. Second example, and we're getting closer to what we're going to look at when we do the matrix product. Sum I equals 1 to n ai bi. So this is getting a lot more abstract, obviously, but again, what am I adding? It's the expression a sub I b sub I, and I is my index. It runs from 1 to n. I don't know what n is here, but let's say it's 2 or 7 or 9, some number, some integer, at least 1. And so I will run from 1, 2, 3, right up to n, and I just replace and add. Okay, so that's what we get. So this will be a1b1 plus a2b2 right up to a n bn, depending on what n is. Okay. All right. So these two examples are a bit more abstract, less concrete than the previous ones, but it's the same thing, right? The principle is always the same. Okay. Are we ready for the matrix product? You know what? I'm going to just start this, but to do this after 50 minutes of online lecturing, I don't know. Okay, we'll see. Okay, so first of all, if I just give you the definition of matrix product, you're going to say, what the hell is that? You know, who came up with this? Well, what's the point? It doesn't seem to, I mean, it just like, it looks completely made up and makes no sense. But it's actually very, very natural. It's not obvious to see where it comes from. Okay, we'll see that a bit later. But here is where it comes from. It turns out that matrices are a very efficient way to represent certain geometric transformations. Think of things like reflections, rotations, things like that. Okay, so you can transform, think of images that you might want to transform. So matrices are a very, very compact, efficient way of encoding these transformations. Okay, now let's say you want to do one transformation and then another. Okay, so it turns out that if you have the two matrices of these two transformations, and you want the matrix of the resulting transformation, how do you get it? It's the matrix product. So this is where it comes from. Okay, so algebraically it looks like what it's not hard to compute. It just looks very strange the first time you see it, but where it comes from is very natural and comes from geometry. Okay, so that's basically where it comes from. So you'll have to believe me for now. Okay, but let's just try to define this. Okay, what the hell? Okay, so ingredients. First ingredient is a matrix of size m by p. I underlined the p for a reason, you'll see in just a sec. Okay. Second ingredient, a matrix that I call b of size p by n. Already it looks weird, right? But there's something in common. It's that p there. Okay. So the product, maybe some of you are freaking out. Don't. Okay. It looks really, but it's not so bad. Okay. So the product AB, that's A times B, is the new matrix whose size is m by n, and the ijth entry. So how do I tell you what a matrix is? I have to tell you what the entries are. So this new matrix, its entry at row I, column J, is that awful looking thing. Okay, so it's the sum k equals 1 to p of a, I, k, b, k, j. That's like half the alphabet is right there, right? So it looks scary, but it's actually not that bad. Okay, well, that's good, right? It was Halloween, so scary is legit, right? That's okay. I'm so funny. Okay, in other words, here's how this works. Okay, so I want to compute the entry that I called Cij of the matrix capital C. I gave a name to my product, okay? AB, I call it C, okay? So how do I get the entry at row I, column J of this matrix? So what you need to do is to take the row I of matrix A, that's the one you see right here. So this is the ith row of matrix A, and you need the jth column. I can't do that with, yeah, right? So it's the jth column of the matrix B. So you get a row here and a column here. And what do you do is you multiply, so that first number with the first number here, then the second number with the second number here, and you keep on going. And of course, what you need for this to work is for the number of entries in a row here to be the same as the number of entries in a column. And that's why I underlined those P there in both. They have to be the same number. And so this is how you get the entry of the new matrix at that. So it's long, right? So if you have big matrices, obviously there's a lot of computations going on, right? Because it'll be a fairly long sum of products for each row and column. You have to do this for each. So that's a lot of computations, but it's not hard. Once you know how to do it, it's really not difficult. Okay. So let's, oops. Yes. So yeah, so first comment is the number of columns of A must be equal to the number of rows of B. So this is, right, if this is going to work, right, you really absolutely need this. So if you look at the definition, that's why that number P is the same. Okay, so A is M by P and B is P by N. Okay, now look at the resulting size. It is M by N. So if you look at the sizes of A and B, the second number here must be the same as the first here. And you want to know the size of the product. You look at the first number here and the last number here, and that's the size of the product. Okay, so here's some examples. Let's say that A is that matrix and B is that matrix. Can I multiply them? Let's see. A is 2 by 2. B is 2 by 3. So yes, I'm allowed to, it makes sense to multiply them because I have 2 here and 2 here. These are the same. So I'm allowed to do A times B. What's the resulting size? It is 2 by 3. Yes. So AB is 2 by 3. By the way, B times A makes no sense. Okay, you cannot multiply B times A. The sizes do not match, right? B is 2 by 3 and A is 2 by 2. 3 and 2 are not the same. You cannot do B times A. It is not possible. Okay, important. All right, so let's see this, and I'll stop after that because it's sort of pointless for you to sort of jump into this and really try to understand it because it's not even on next week's test, right? So you have other things to do, but I'm still giving you the definition, and when we come back after the test, I'll go over it again. And okay, so if this is A, this is B. Again, A times B is 2 by 3. Okay, so let's compute the entry at row 1, column 3. So this is row 1 of A times column 3 of B. So what's row 1 of A? It's 1, 3. Column 3 of B is minus 4, 6. So I'll do 1 times minus 4 plus 3 times 6. That's 14. Okay, so it's hard to, I mean, it's not obvious to get a meaning out of that number, right? So what does that number mean? Again, it makes sense in a context of geometry, but it's like sort of far away. It's really, it's not like a direct, obvious link from the algebraic operations that we're doing to the geometry. Okay, so just see it now as a formal game. That's the game, that's the way it's played, and that's it. But there's a meaning behind it, okay? But it's not immediate. Okay, so if you compute all the entries of the product, this is what you'll get. So for example, where does this 11 come from? This is row 1, column 1. So I take row 1 here, column 1 here. So it's 1 times 2 plus 3 times 3. So that's 11. This is where this 11 comes from. And you do that for each of these entries. Okay, that's how you get the product. All right. Okay. So Okay, I'll stop here. I'll just stop here, and we'll take this over again when we not next week, but the week after. Okay, we'll go over this again. I've opened up 2 new web works for this week. They are very short, but they are relevant for your test. If you have questions, comments, I am here, available. So that's it for today. Oh yeah, Thursday, I will be solving problems for test 2, right? So I'm going to do all sorts of problems related to the material for test 2. I've posted extra problems for test 2. Don't forget the book. Also, you have lots of problems in the book. So yeah, is that good? All right.
Yeah, it's good. Yeah,
Okay.
yeah.
Yeah, man. It's just yeah. I will stop recording right now.